In this video, we're looking at a uniform circular motion, circular orbits problem, and we're given a little bit of context on this. This is about the Lunar Reconnaissance Orbiter, or LRO, and this was a spacecraft launched in 2009 to take topographical measurements and look for water ice on the moon. So we're told it's orbiting in a very nearly circular orbit around the moon with an average altitude of about 90 kilometers above the surface. And we're given data below the picture for the radius of the moon and the mass of the moon. Now, one of the first things we want to do here, just so we don't run the risk of forgetting, is that with an altitude of 90 kilometers above the surface, we have to add that to the radius of the moon to get the total orbital radius. So that gives us 1,827 kilometers. Incidentally, that's about a 5% difference in the orbital radius compared to using the radius of the moon itself. So in part A, we're asked to get the orbital period of the LRO. And the point is not to quote some previous result here where the orbital mechanics problem was already solved. The point is to work from first principles, and that means we start with a force diagram. So there's the force pointing to the center of curvature, in other words, the centripetal force, that causes the path of this orbiter to bend into a circular path. And that force, of course, is caused by gravity, so I'll call it Fg, and it points to the center of the moon. The magnitude of that force is given by Newton's law of gravitation, and that's G, big M for the mass of the moon, little m for the mass of the orbiter, and then divided by r squared, where that's the orbital radius. And we recall that G is approximately 6.67 times 10 to the negative 11. And the units there are Newton meters squared per kilogram squared. Okay, so that force causes the centripetal acceleration. And before we put it all together, I want to look at that centripetal acceleration. The formula most of us have memorized is v squared over r. But we can rephrase this in terms of the period, which is going to be convenient for answering part A. So we relate the speed to the period by saying the speed is just the distance traveled divided by how long it takes. And if we do this on one orbit, the distance traveled is 2 pi r, or the circumference of that orbit. The time it takes is 1 period, capital T, and we're going to square that, and then we still need to divide by r. So squaring that, we get 4 pi squared r squared over t squared, and then there's an r in the denominator that's going to cancel out. So we get 4 pi squared r over t squared. Now it's time to put it all together, and for this we use Newton's second law. So I can say that F net equals ma for this orbiter, and the net force on it, there's only one force acting, and that's the force of gravity, so that's gmm over r squared. And then the mass of the orbiter is little m, and its acceleration can be written as 4 pi squared r over t squared. Now it turns out the mass of the orbiter is irrelevant. We see that canceling out of the algebra. And what we're trying to solve for here is the period. So I need to multiply both sides by t squared, divide by big M and G, multiply both sides by r squared, and square root the result, and I'll get t. So again, surviving in the numerator on the right-hand side, I still have a 4 pi squared. And there was an r there, but when I multiply by r squared, that becomes an r cubed. So that's in the numerator on the right-hand side. Then in the denominator on the right-hand side, well, I had to divide by a big mg, where big M is the mass of the moon. So we're ready to plug everything into this, and we need to convert to SI units. That means that radius, the orbital radius, should be expressed in meters. So it was 1,827 kilometers. We just have to tack on 3 zeros to get meters, and we need to cube that. Then our mass is 7.342 times 10 to the 22nd, and big G, 6.67 times 10 to the negative 11. When we run the numbers on this, we get about 7,012 seconds. And it's probably better to express this in minutes. So we divide by 60, and we end up with about 117 minutes. All right, so the LRO goes around in a little less than 2 hours. The next part of the question asks us to get the speed of the LRO in its orbit. And so we're just going back to this idea that happened in the second line, where we relate the speed to the orbital radius and the period. Again, the speed is the distance traveled divided by how long it took, so that's 1 circumference divided by 1 period. We plug in the orbital radius in meters and the period in seconds, and we're staying in SI units here, so that's 7,012 seconds. And when we run the numbers on this to 3 significant digits, we get 1,640 meters per second. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.